Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Kohat University of Science and Technology. I welcome you to the course PHY 103 Waves and Oscillations. Today I will be covering the 12th lecture of this course, and the topic is Energy and Power of a Wave Traveling Along a String. First, I will give the learning objective. At the end of this presentation, the student will know how the energy and power transport through a wave along the string. In this course, we are following the book Fundamentals of Physics by Holliday, Resnick and Walker, 10th edition. Some of the illustrations are taken from this book. We will start with this question. Can we apply the energy description of simple harmonic oscillator for the waves on a string? If you remember, in our previous lecture, we have discussed how the energy, the kinetic energy, and the potential energy varies for the harmonic oscillator, such that their total energy is the sum of the two energy, and that remains constant. So the question is, can we use this description for waves on a string? So to start with this, let's say we have this wave traveling along the positive x direction, having wavelength lambda as marked, and we have these random positions A and B on that string, having small length. Now the question is, can we describe the waves through this kind of energy? As in this presentation, we will be trying to analyze the energy and power transports through a wave. So if we just block that string over which the sine wave is propagating now, and we have a small slit through which we only see this portion of the wave. For example, this is just a random portion, and we mark that portion so that this is visible to us through that slit. Now when the oscillations start on the string, and we have, and that wave is propagating along the string, but only this portion is visible to us, so that portion will look like performing simple harmonic oscillations as shown here. That is, it will oscillate between the extreme position, the plus ym and minus ym, and this is like a simple harmonic oscillator. This small portion is like a simple harmonic oscillator, such that at the extreme point, that is in our cases previously that was xm and minus xm, but here we have ym and plus ym and minus ym, such that at the extreme position the kinetic energy is zero, because at this point and at this point this object is at rest, so that's why the kinetic energy is zero, and the potential energy is maximum at the extreme points, because we have discussed the mass attached to the spring, so more stretching or more displacement give rise to more potential energy. And at this position where the stretching is almost zero at the equilibrium point, so that potential energy is zero here and maximum at the extreme points, as clear from this graph, and the kinetic energy is zero at the extreme point and it is maximum here. So the question is, can we just describe the same energy description for the harmonic oscillator? That is, the description is valid for this whole wave. So the answer is no. This is not a valid description for the energy of a wave, because this is not a single element. This is just a small portion of the wave, and this is a continuous object which is connected to the rest of the wave. So individually, the small elements are performing harmonic oscillations, but the energy is not varying the way it was varying in the simple harmonic case. So that the motion of this element influences the motion of the uh, other elements on the string. So that's why the energy description is not the same as that for the harmonic oscillator. So now we will see how we can describe the energy and then power of a wave traveling along the string. So we have a string here over which we have marked just two random spots, A and B, having equal length element dx, right? And there is a sine wave propagating along that string, propagating along the positive x direction. So we will see first how the kinetic energy and potential energy description is a valid description for a wave traveling along the string. So let's say at point A, the transverse velocity is 0, that is beyond this point, as we have seen on the previous slide. Beyond this point and this point, the velocity is 0. The beyond this point, the object is not moving up, so that the transverse velocity is 0 at point A. So when the velocity is 0 there, so it means the kinetic energy is also 0 at point A, and also this is almost the same point on the other point, on the other side of the equilibrium point. Now, so that means kinetic energy is 0 at point A. Similarly, the elastic potential energy is 0 at point A, because this this wave is generated because of the tension in the string. So the elastic potential energy is 0 here, because this element is not stretched at this state, that is at this random position. When once the element of that string have this kind of position or this kind of position, this is an unstretched state, so that there is no stretching, means there is no elastic potential energy associated at this position, so that the potential energy is also 0. So at point A, velocity is 0, so that kinetic energy is 0. At point A, the stretching is not there because of the tension, because this is a relaxed position, so that the potential energy is also 0. So the total energy is also 0, because total energy is the sum of the kinetic energy and the potential energy. So that was not the case in the simple harmonic oscillator, but in this case the energy simultaneously goes to 0, either the potential and the kinetic, and hence the total energy is 0. So we can say that elements on a string having this state of motion will be having 0 kinetic energy, 0 potential energy, and 0 total energy. At point B, this is another point having the same length, but at point B, the transverse velocity is maximum, because at these extreme points it is 0, and here is having maximum velocity. So once the velocity is maximum, it means the kinetic energy is also maximum at this point. Similarly, the elastic potential energy is maximum at this position, because if you see, these are dx length, but if you see, this is a bit in stretch form, say that this length looks bigger here. The same length element is now looks in having more length because of the tension in the string at this position, so that once the stretching is maximum, it means the elastic potential energy is maximum, so that the total energy, which is the sum of the kinetic energy and potential energy, will also be maximum at position B. So this is the valid description for the energy description of a wave traveling through a string. That is the total energy, the kinetic energy, and the potential energy goes to minimum at points, and then at the other point it goes to maximum at the same time, which is not the case for the harmonic oscillator description. So now we will verify these things mathematically. So we'll start with the rate at which kinetic energy transmit through that string. So we consider that string the same string, and we mark just a random spot having length dx. This is a small element of length dx and having mass dm. So because of this element, how much kinetic energy is transmitted, that is small kinetic energy dk. So we need to convert this dm in terms of the linear mass density, such as mu is mass per unit length, so that this dm can be expressed as mu dx. Similarly, this u is the transfer velocity, so that the wave is described by y is equal to im sine of kx minus omega t in our previous lecture, so that we can find out the velocity by differentiating this with respect to time. So if we differentiate this y with respect to time, we can have u, and we need u square and then also dm. So putting those values here, one can have this half the value of dm and also the value of the u square. Now we are interested at the rate at which kinetic energy is carried along the wave. So that is equal to the dk over dt, that is by dividing dt across the equation, so that this half, this mu is the same, and dx by dt is the rate of change of x. So that means that is the wave velocity. Dx over dt is the wave velocity, so that here this dt will be there, so that it gives us the rate at which the kinetic energy is transferred across the wave, and this v will be because of the dx over dt. So this is the form of kinetic energy at the rate at which it flows through this. So one can see that this depends upon this harmonic function and x and t. Now if you remember on the previous slide, we have seen that these values are the same. It goes to 0 and it goes to maximum value at the same time. So now we are we want to find out an expression for the potential energy as well. So for that we need to consider a random point on this string, such that the tension, which is the force, the work done by the tension will be equal to du, the energy stored as elastic potential energy, so that generally work done is the force times the displacement, so that the force is the tension in the string and the displacement is this dl is the stretch length of the string, and when it is in the unstretched situation, for example, this is the unstretched situation and this is a stretch situation, so that it goes up a bit so that we have a dy here. So that the stretched length minus the unstretched length will give rise to the amount of displacement that is there because of this tension. This is a small portion, so but we have shown this here just to visualize things. So now if we just use the figure to convert this stretch length by dx square plus dy square will be equal to the dl square under the root, and this dx will be the same. Now we need to mathematically simplify this expression by taking the dx common, so that we are left with this expression, and then using the binomial expansion such that this dy over dx is a small thing, so that one can ignore the higher terms. This 1 and 1 will be cancels out, and we will be left with this thing. Now in order to find out a similar expression, so that we can transform this tau into v, such that this tau will be equal to v square into mu, so that this will be converted. And also we have u, so that if we differentiate with respect to x, so that, and then square it, so that there will be a k square. So that k square can also be because in this expression there is no k, so we want to just to make sure that the two expressions are the same. So using these definitions over here, one can have the similar expression for the rate at which the potential energy transmit across the wave. So that means the two energy are equal, and the total energy, the rate of the total energy will be equal to the sum of these two rates, so that this half and this half will be 1, and the rest of the thing will be the same. So on a previous slide we have discussed that these energies, the potential energy and the kinetic energy, goes to 0 at point like this, and it goes to maximum value at point like this, and such that the total energy is the sum of the two energies. Now as we have derived, the two rates are equal, and equal to half. Mu is the density of the rope, v is the velocity of the wave which is traveling along that, or this is the angular frequency at which the oscillations are governed, ym is the amplitude, and then this is a cos square factor. Since when dealing with harmonic functions, periodic functions, it is better to find out the average value. So the average rate at which the kinetic or the potential, since the two are equal, energy is transported. So for that we need to find out the average value. So for that, these things are constant. So only this this function varies over one orbit. So in order to calculate the average value of this thing, so this will be the same, and this cos square x, this is the definition. So if you calculate, then this comes out to be 1/2. Now, so that the average value, whether kinetic energy or the potential energy, since they are equal, that will be equal to half mu v omega square, and the average value will be equal to 1/2, so that this will be 1/4. The cos square average is 1/2, so this will be the average value of the kinetic energy at which it is transported. Now the second thing is the power, which is the average rate at which energy of both kinds is transmitted by the wave. That can be the sum of the two energy, the kinetic energy and the potential energy. Since they are equal, so one can stick to one of the energy, so that this will be 2 times. As we have discussed on the previous slide, the total energy is the sum of the two energy. So if we put this average value, average rate at which the kinetic energy is transported over here, so that the average power expression comes out to be 1 over 2 and then mu v omega square ym. So the average value, this is the average power per cycle. Remember, the cycle is 0 to 2 pi. This is the power which is transported by the wave per cycle. Now, this power, which is half m v omega square y m square, is transported along the sine wave. As I told you, this mu is the mass density of this rope. This v is the velocity at which the wave is traveling along the string. Omega is determined by the oscillations provided by this gentleman to move his hand up and down, so that would be a linear frequency, and from there one can find out the omega by multiplying it with 2 pi. And this ym is the amplitude of the wave on the rope. Now one can see that this average power depends upon this mu and v. These two depends upon the material and tension in the string. Since we know that in our previous lecture that the velocity of the wave along the rope is proportional to the tension and mu, so that this mu is the density of the rope. So different density, a rope with different density will transport different power, keeping all the other elements same. And also this v is there, so that it also depends upon the tension in the string. The other two factor, which is the angular frequency and the amplitude of the wave, that is depends upon the process at which the wave is generated, right? As I told you, this omega is related with the number of cycles per second, number of oscillations per second, so that frequency can be converted to mu. And this ym is also depends upon the generation mechanism. So we have total 4 quantities over which this power depend, in which this mu and v depends upon the material, and these two, the other two, depends upon the generating mechanism. Now, the dependence of the average power of a wave on the square of the amplitude and also square of the angular frequency, these two terms. This is a general result, and this is true for all kinds of wave. That is, this is not only valid for a wave traveling on a string, but the average power for sound waves will also be proportional to the omega square ym. The light waves will also proportional to this thing. For any kinds of wave, this power will be proportional to the square of the amplitude of the wave, and also it will depend upon the angular frequency. Now these two factors will change with different once we are discussing different types of wave. For example, in sound waves, this mu, which is the density of the rope, will be changed to the density of the air. For example, the sound waves are traveling in the medium air, so that this will be the density of the air, and this v will be the sound velocity, sound speed, and these two will remain the same. They're similarly for the electromagnetic waves and for all kind of waves. So this topic, which is energy and power of a wave traveling along the string, this average power is somehow valid for all kinds of description, and of course these relevant parameter will change once we are discussing different types of waves, but the in principle this is the same for all kinds of wave. Now we will be solving a simple problem, which is simple problem 16.3, and the statement is a string has a linear density. This is the density of that rope, mass density, is under the tension 45 Newton. Okay, over that string, we send a sinusoidal wave with a frequency 120 hertz. That is, in 1 second, the rope is oscillating 120 times. So that the amplitude it requires is 8.5 millimeter. Now we need to find out at what average rate does the wave transport energy. So this is taken from your course book, Fundamentals of Physics. So imagine this thing, that is this man oscillating his hand 120 times per second. Just imagine he can do that, so that the amplitude of the wave is this much, the mass density or mass per unit length of this rope is this much, the tension in the string is this much. So with this situation, how much energy is transported across this rope? To solve this, we need to start with the average power, which we have just discussed. So in this expression, the Ym is given, the linear frequency is given. From there one can find the angular frequency. The mu is given. We don't have the V, so we need to find out V and omega first, so that we will be able to calculate the power. So the first one is the angular frequency. The linear frequency is this much, so that 2 pi times the linear frequency, that will give rise to 754 radian per second as the angular frequency. Similarly, we have the mass density and the tension, so that the velocity can be calculated as this much. So the velocity of the wave will be 9.2 meter per second. Now using these data and also the given data, one can find out the average power, which is around 100 watt. So with this situation, the power that it can transport along that string will be 100 watt. Now you need to solve these two problems, which is based on the energy and power transport along a string. So you need to solve these two problems in order to understand the concept of energy transport over a string. So with this, I thank you for your time.